Okay, one of the things you're going to have to know for tomorrow when you come into class is some important facts about correlation. Alright, correlation and regression describe only linear relationships. Predicting outside the range of the available data is risky. Both correlation and regression are strongly affected by outliers. And the least squares regression line, the LSRL, that's your line of best fit, always passes through the point x, y. I should put that it also passes through the coordinate point of the y-intercept, so 0a. Whenever you figure out your LSRL, always plot your x bar, y bar point, as well as the y-intercept, and then connect the two. And then finally, switching the x and y will have no effect on the correlation, but it does affect the least squares regression line. Okay. The next thing I want to talk about is the residual. Now the residual basically is this right here. It's the distance from this right here. I'm going to call this point right here. This is the observed y. That's the observed y. Okay. What I'm going to do is I'm going to draw a line straight down to the line of best fit. Now, whatever this coordinate point is, okay, that's going to be x, comma, y. That y right there, let me put a little mark there, or let me draw an arrow here. Let's see. Let's put there. So this one right here is talking about that point right there. Now, when I look at the y value, okay, when I look at the y value, this right here, this is going to be the predicted y. So this one right here is the observed y. All right, this is going to be x, comma, y. So this y is going to be the observed y. This y is going to be the predicted y. In order to find the residual, which is the distance between the two, you got to take the observed y minus the predicted y. And we'll go over that tomorrow when we go over your tape or what we did today. Now, the next thing I want to cover is the residual plot. What you're going to do is you're going to create what we call a residual plot. And I'll show you how to do that here shortly. Basically what this does is it helps us determine how well the line of best fit describes the data. If it is a really good description, it's going to give you no obvious pattern. This is the ideal situation. This is what I want to happen. However, when you create your residual, now look, this is your residual, all right? This is the distance. If it gives you a pattern sort of like this, it is not linear. Therefore, it is not the R value that we have, or the line of best fit, is not a good fit for our data. And then the residuals should be relatively small, okay? And we'll talk about that more tomorrow. Now, the next thing we're going to talk about is R squared. Now, we've been seeing R squared whenever we find the line of best fit. So far, we've done the correlation. And then right below it on the graph, or on the calculator, is R squared. R squared is the numerical quantity that tells us how well the least squares regression line predicts values of the response variable y. In other words, how good is our line? So not only do we have the residual plot to help us, but we also have R squared. Now R squared is the fraction of the variation in the values of y that is explained by the least squares regression line of y on x. This is more like lawyer talk. We'll go over what I really want you to write down and what I want you to say based on the R squared that we get on the calculator. Now the next thing I want to talk about is what we did today. Notice I talked about how the increments should be fairly nice and neat. We drew a line of best fit, and let me go ahead and draw one here. The line of best fit started from here. It went through the point x bar, y bar, so about 4.8. So it went about right here. Okay. Now with this, I could find the residual, which is the distance from the observed down to the predicted. Remember, this is the predicted line. All right. A couple other things. Remember, the number of beers consumed is your explanatory. This explains the blood alcohol content. The blood alcohol content depends on the number of beers consumed. Next, this is the backside. What is the LSRL? In our case, it was y hat is equal to negative 0.01 plus 0.02x. What is the correlation? The correlation was 0.89, which gave us a strong positive linear correlation. Now, I asked you to interpret the slope, and we did that for most of the classes today. 0.02 over 1. Notice this part is my slope right here, okay? 0.02. So what does that mean? 0.02 over 1 means for every one beer a person in the study consumes, the blood alcohol content will increase by 0.02. So for every one beer, that's what we're talking about right here. So for every one beer right there, the blood alcohol content increases by 0.02. Now, interpret the y-intercept. So if you were to draw a graph and label the graph right here, 0, negative 0.01, that's where it would show up. What this means, in the study, a person who consumes 0 beers will have a starting blood alcohol content of negative 0.01. Now, mathematically, this makes sense. However, we know that in real life, you can't have a negative blood alcohol content. Now, what would the blood alcohol content be if a person drank 13 beers? Well, algebraically, what we do is we take our line of best fit, our equation of the line, our LSRL. We plug in 13 for x, and then we end up getting y hat is equal to 0.25. If done by hand, this will be 0.25, so the blood alcohol content is 0.25. Now, if I were to use the calculator, all right, I'm going to hit calc. I'm going to hit regression, x, a plus bx, copy. All right, so there's my equation of the line. I'm going to go to menu. I'm going to go to number 5. There's my equation. I've selected already. I'm going to hit draw. All right, notice it only goes from 0 to 10. I'm going to increase my window to 15, so my x value is 15. Now, I'm going to use the feature shift trace. So shift trace. I'm going to type in the number 13, okay, and hit enter. What that is telling me is this. A person, let me do this again. Let me get my window here. Let me increase this to 18 so I can see it on there. All right, again, I'm going to shift trace. I'm going to plug in 13. So a person who drinks 13 beers should have a blood alcohol content of 0.22. All right, so that's what I would put here. Yep, sorry, I don't need that. I would put y is approximately 0.22, or y hat. Okay. Let me go ahead and put my little hat on there. All right, so your y hat would be approximately 0.22. All right, let's move on. All right, let's look at H. If a person has a blood alcohol content of 0.21, approximately how many beers does that person drink? Well, I'm giving you the blood alcohol content. So blood alcohol content, we're going to substitute 0.21 in there. Bring down to negative 0.01 plus 0.02x. Algebraically, this is how I'm going to solve it. I'm going to add 0.01. I get 0.22. Bring down my 0.02. I'm going to divide by 0.02, and I get 11. So technically, by hand, a person who has a blood alcohol content of 0.21 should drink approximately 11 beers. Now, if I do this by calculator, I'll get a different story. So I'm going to hit exit. I'm going to drop down to the y equals 0.21. I'm going to create another line. Now notice I can find the intersecting point. So come over here to GSolve, find intersection. So a person with a blood alcohol content of 0.21 will approximately have would have drank 12.39 or about 12.4 beers. So you can probably round that up to about, or round that down to about 12. So anywhere between 12 and 12.5 beers. And that, ladies and gentlemen, concludes